All right, we're in section 12.1 where we are going to explore solids. So, up to this point, we have dealt with exclusively two-dimensional items. So, you know, we looked at area, we looked at um, of different shapes, different sizes and stuff like that. So now we're going to dive into the three-dimensional world, and uh, the first thing that we're going to look at when it comes to exploring uh, solids and three-dimensional objects is be able to discover what is a polyhedron. By definition, it says a polyhedron is a solid bounded by polygons. So what you have to look at is each of the surface objects for each three-dimensional object, and if you can say that each surface is a polygon, then you can say that that solid is a polyhedron. So we have a series of shapes here, and so what we can do is first off, let's just label them. Let's go A, B, C, D, E, and F. So from here, we have three of these solids are polyhedrons. Three of them are not. So hopefully you can render your best hypothesis to be able to figure out which ones they are. So the ones that are not polyhedrons are anything that has some type of curvature to it. So this sphere is not, so this would be no. This cone right here because would be a no, and this cylinder here would be a no. Examples B, C, and D are in fact polyhedrons because, like for instance, if you look at example B, every surface area shows up as a rectangle or at very least quadrilateral. Depending on my drawing, it's probably not that great. The next one is a pyramid. The base on the bottom is a rectangular or a square, and the the triangles that are on top show up as triangles. On the value for D or polyhedron for D, I got two bases as triangles, and then I got these lateral faces as rectangles. Okay, so what we're going to look at here is we're going to look at for the ones that are polyhedrons, so examples B, C, and D are polyhedrons, we want to find the number of faces, uh, vertices, and edges. So let's just go, I'm going to go B, C, and D. So faces. So I want to find the faces for B. So I have one face here, so that's 1, 2, 3, 4, 5, and then 6. So I have 6 faces for um, that prism. The vertices are each point on the shape. So I could say I got 1, 2, 3, 4, 5, 6, 7, and 8. So I have eight vertices and edges. So I go back up here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I got 12 edges there. Looking at C. So going for the faces, I got one face as the base. I got one. I got two, three, four, and then five. So I got five faces for C. How many vertices? I got one, two, three, four, five. And finally, edges. Count them out. I got one, two, three, four, five, six, seven, eight. So I got eight. And then the final one, look at the bases. So I got one here, two, three, four, and five. So I have five faces. Vertices, I have one, two, three, four, five, six. And edges, we have one, two, three, four, five, six, seven, eight, nine. So nine. Okay. You could, count a majority of these out to be able to figure out what the faces, vertices, and edges are. But we also have what is called Euler's theorem. Euler's theorems that we can figure out the number of faces, vertices, and edges of a polyhedron by relating it to the formula of faces plus vertices is going to be equal to edges plus 2. So coming over here, I got 6 plus 8 because this was the face, this was the vertice. It's equal to the edges, which is 12 plus 2. Do we agree that 14 equals 14? Yes, it does. And you can check C and D to see if they in fact do work. So if you can just go here, it's 5 plus 5 is equal to 8 plus 2. 10 equals 10. And I have 5 plus 6 is equal to 9 plus 2. So 11 equals 11. So it checks out there as well. All right, so if we look at this problem here, it says how many faces, vertices, and edges does a hexagonal prism have? Okay, so a lot of times what I like to do is I like to draw these out. So a hexagonal prism means that it has a hexagon as a base. Hexagon means that it has 6 sides for that base. So, you know, let's draw this out. So you can go 1, 2, 3, 4, 5, 6. So I got one base. And then I'm just going to go here, 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 and here. And just kind of draw this out. So I got 1, 2, 3, 4, 5, 6. And then I just kind of represent those as dashed lines. So just to kind of get an idea of what the design is. And then I'm going to go here and I'll do faces. So I'm going to say this is 1, 2, and there should be 6 lateral faces on there. So I'm going to have 8 faces for this particular example. My vertices, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I got 12 vertices. Now from here, we can now implement Euler's theorem and say, okay, I got 8 plus 12. That's going to be equal to whatever how many edges it has plus 2. So this gives me 20 is equal to E plus 2. Subtract 2 to both sides. That means that there is going to be 18 edges. Another thing that kind of comes back, we have different different classifications for certain 3D objects. One of which is a 3D object can also be um, convex or it can be concave. So if we remember when we looked at a two-dimensional object, anytime you had a convex shape meant that if you were to almost take like a straight edge at each edge and the straight edge did not cross the center at any one of those edges, you could say it was convex. If you looked at concave, and if you could say just one edge across the middle like it did here, so this would be the convex, this would be the concave. Kind of similar idea when it comes to three-dimensional objects. Usually it's attached to what does the base look like. So if you have, um, well, for example, all of the polyhedrons that we had here would be examples of convex, um, convex 3D objects because there's nothing that any of these surface values that would make it a concave polygon. So if you wanted to look at a 3D shape that was convex, you'd like say, all right, well let's make a base that is concave. So if we go here, 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 and here, and then make our shape off of that. So we would just go up, up, and then try to mimic the shape up on top. Easier said than done sometimes. So it looks something kind of like that. And because of this portion right here that kind of protrudes on the inside, makes that 3D image concave. All right. Last thing here is talking about cross section. Cross section is taking slices out of 3D object. And what the main idea of this is asking, okay, what is the shape of the cross section that you get? So it'd be almost like, okay, if I took like a knife and I cut through a portion of whatever 3D object it happens to be. So if I were to cut, you know, make a cross section of this cube, so remember cubes have, distances that are all the same length, width, and height. If I were to take a cross section of this shape, which would be a 2D object, would be a square. Out of this cone, if I take a cross section here, this shape right here would be a circle. And that is being able to explore solids. Hope this helps. Till next time.